Have you ever, just stopped and thought about how your phone unlocks, sees your face, bang, it's open? Or how your virtual assistant understands you even when you're kind of mumbling first thing in the morning?
It's pretty incredible, isn't it? Feels seamless.
Totally. This AI power, it's woven into everything, makes really complex things feel, well, easy. But here's something that really got us thinking for this deep dive. A surprising fact. For all that smartness, today's AI, it uses massive amounts of energy, often way, way more than your own brain doing the same job.
A lot more. That energy cost is a huge bottleneck right now.
Okay, so let's unpack that. Today we're diving into this really fascinating field. It's called neuromorphic computing.
Sounds a bit technical, maybe.
Yeah, maybe a little, but the idea is simple. Think of it like building computers that actually work like brains. Not just software acting like a brain, but the hardware itself being brain-like.
Right, building the structure, not just simulating it.
Exactly. And the secret ingredient, something called spintronics. It's cutting-edge stuff using tiny, tiny magnets.
Tiny magnets doing brain work. Okay.
So, our mission today is to figure out how scientists are using these magnetic bits to build these brainy computers. We want to look at the results they're already getting, which are frankly astonishing, and explore why this could totally change the future of AI. We'll be looking at a couple of recent scientific papers that really shed light on this.
Sounds good. And yeah, starting with that energy problem is key. Because current AI, the stuff on our phones, our cars, it's powerful, no doubt. But it mostly runs on traditional computers, digital ones. And they're built very differently from our brains.
Based on that von Neumann architecture, right?
Exactly, the von Neumann architecture.
Yeah.
And that fundamental difference is why they're such power hogs.
Okay, so why is that specific architecture so thirsty, energy-wise?
Well, think about it like this. In a normal computer, you have the processor, the part that does the thinking, and the memory, where the data is stored in separate places. It's like having your library and your reading desk in different buildings. Every time you need a fact, you have to run to the library, get the book, run back, read it.
Ugh, all that back and forth. That takes time and energy.
Precisely. It's called the von Neumann bottleneck. It wastes a huge amount of energy and slows things down. Our brains, though, they mix memory and processing much more closely. Super efficient. And researchers like Christopher Merrows and his team at the University of Leeds in the UK, they pointed this out really clearly in Nature Communications. They said current AI simulations use power consumption several orders of magnitude greater than biological brains doing the same thing.
Orders of magnitude. Wow.
Yeah. So the goal, as they put it, is dramatic reductions in power consumption. And you get that by building hardware that works in a neuromorphic manner natively, mimicking the brain directly.
So it's not just about smarter code, it's about building smarter, brain-like hardware. Which brings us to spintronics. Sounds like something out of sci-fi. What is spintronics exactly?
It does have that feel, but it's real physics. Basically, you know how electrons have an electric charge? That's what we normally use in electronics.
Right.
Well, electrons also have another property called spin. You can think of it like each electron being a tiny spinning magnet, like a microscopic compass needle.
Okay.
Spintronics is about using that magnetic spin along with the charge to store and process information. It opens up totally new ways to handle data.
Using electrons as little spinning magnets.
Yeah.
Okay. Why is that specific property, the spin, so useful for making brain-like computers?
Because magnetic materials, the kind used in spintronics, naturally have properties that are, well, perfect for mimicking brain functions. For instance, they have memory. They remember past states. That's called hysteresis. Very brain-like.
Like forming memories, yeah.
Exactly. And they react non-linearly, meaning they don't just respond proportionally to input. They need a certain threshold before they fire strongly, just like a neuron.
Ah, okay. The all-or-nothing firing.
Right. Plus, they show collective behavior, lots of tiny magnetic bits influencing each other. And crucially, they're non-volatile.
Meaning they hold information even if the power goes out.
You got it. No constant power needed just to remember things. Merrows and his colleagues point out these features make spintronics ideal. The hardware inherently behaves in brain-like ways.
So the material itself does the work instead of needing layers of code to fake it. That makes sense. Okay, let's talk brain building blocks then. Synapses, those connections between neurons. Their weight or strength is key for learning an AI, right?
Absolutely critical. Synaptic weights are how AI models learn and adapt.
But there's a problem with standard magnetic memory, these things called MTJs, magnetic tunnel junctions. They usually only have two states, on or off, 0 or 1.
That's right. Binary.
Which isn't really how brain synapses work, is it? They seem more analog, more nuanced.
Exactly. You often need many possible weight values for a synapse to do complex learning. And as Merrowes et al. Explain, with binary MTJs, you'd need many binary MTJs to store a single synaptic weight.
So it becomes really bulky and inefficient just to represent one connection properly.
Precisely. It was a major roadblock. But this is where another team comes in. Led by Peter Restut from AGH University of Science and Technology in Krakow, Poland. They published some really exciting work in a paper called Multi-State MRAM Cells for Hardware Neuromorphic Computing.
Multi-state MRAM. Okay, so they tackled this only two states problem. How did they do it? What was the trick?
Their solution was actually quite elegant. They developed these multi-state MRAM cells. MRAM stands for Magnetic Random Access Memory. And they did it by connecting multiple standard MTJs together in series.
In series, like one after the other, like beads on a string.
Exactly like that. Imagine linking several tiny magnetic switches in a row. Each switch can be on or off, right? But the total resistance of the whole chain depends on how many switches are on versus off. So the chain, as a single unit, can have multiple distinct resistance levels.
Oh, wow. So instead of just on-off, the whole chain gives you steps, like a dimmer switch instead of a simple toggle.
Well, that's a great analogy. Yes. Their design means a single multi-cell made of N MTJs can have N+1 different states.
N+1. So if they link, say, 7 MTJs.
They get 8 distinct states, 8 possible synaptic weights from one compact unit. They experimentally proved this worked with up to 7 MTJs.
That's huge. Much more compact, much more efficient than using lots of binary ones.
Absolutely. And really importantly, they note these spintronic multicells don't have the endurance issues some other memory types have. They can be written to many, many times. Plus, they're compatible with CMOS technology.
Meaning they can work with standard computer chip manufacturing.
Yes. That's a massive advantage for actually getting this stuff built and into devices. It's not some exotic material needing whole new factories.
Okay, so we've got these efficient multi-state connections, the synapses. What about the neurons themselves, the parts that add up the signals and decide whether to fire?
Right, the other half of the equation. Biological neurons basically add up the weighted inputs they receive. If the total hits a certain threshold, zap, they fire an output signal.
How do you mimic that with spintronics?
Well, Merrowes et al. Describe how spintronic devices can naturally mimic what's called the leaky integrate and fire model, LIF. It's a common way to model neurons. Think of it like a bucket filling with water, incoming signals. But it also has a small leak. If the water level hits the brim, the threshold, it spills over, fires.
Okay, I can picture that.
Spintronic components can do this using their magnetic state. The magnetic state integrates the inputs, but also naturally decays a bit, like the leak. If it hits a magnetic threshold, it flips, sending a signal. And there is a team in Poland. They didn't just make the multi-state synapses. They actually designed and built a complete hardware artificial neuron.
The whole thing.
The whole thing. They used their multi-state MTJ cells for the synaptic weights, plus standard CMOS circuits to do the summing up, and importantly, a circuit to create that nonlinear firing decision, the sigmoid function.
Wow. So they built the connections and the processor, a little piece of artificial brain hardware.
Pretty much. A fundamental building block.
Okay, so the ultimate test then. Does it work? Did they try it out on a real task, something recognizable?
They did, and this is where it gets really compelling. They built a neural network 4 layers deep using these spintronic synapses and CMOS neurons. And they tested it on recognizing handwritten digits from the MNS database. That's a classic AI challenge, reading numbers scribbled by different people.
Right, I've heard of MNIST. So how did their hardware brain do? Was it accurate? And what about the energy?
The results were, frankly, stunning. Using their multi-cells with 4 or more MTJs linked together, they achieved a detection ratio comparable to the software algorithm. The error rate was below 3%.
Below 3% on hardware. That's amazing. That's practically as good as the software versions, right?
Almost exactly. But running on this super efficient brain-like hardware. And now for the energy part, the real kicker. To process one image, a 20 by 20 pixel digit, their circuit used only 37.4 picojoules of energy.
Picojoule. That sounds incredibly small.
It is incredibly small. To give you some context, they compared it to another hardware designed by Zhang et al. That one processed a smaller image area, only 10 by 10 pixels, and used 194 picojoules.
Whoa. So Rezut's team processed 4 times the area using, what, like a fifth of the energy?
Roughly, yeah. It's a massive leap in efficiency. Plus, it was fast. They measured the time to process one image to latency at about 1 microsecond. Basically instant.
Accurate, incredibly energy efficient, and super fast. Okay, that does sound like a potential revolution. And you're saying this isn't just happening in one lab in Poland, others are seeing similar potential.
Yes, absolutely. The field is moving fast. Meros and his co-authors also highlight other promising results that show commercial interest is growing. Like a U.S. Air Force-funded project at Princeton hit over 90% accuracy on a different image task, CFAR-10, using MRAM. And a collaboration between Samsung and Harvard got almost 99% accuracy on MNIST using MRAM chips made by Global Foundries, a major chip manufacturer.
Yeah, it's Samsung, Global Foundries. Okay, so big industry players are definitely involved now. These aren't just academic curiosities anymore.
Exactly. These are proofs of concept moving towards real applications.
Which is super exciting. But, there are always challenges with new tech. What are the main hurdles still facing spintronic neuromorphic computing before, say, it ends up in my phone?
Oh, for sure, there are challenges. Big engineering challenges. Meros, et al. Discuss some key ones. One is just scaling up. How do you connect billions, maybe trillions of these tiny synapses and neurons together reliably and efficiently? That large-scale connectivity is tough.
Wiring up a brain is hard, yeah.
Then there's sensitivity to external magnetic fields. You don't want your brain chip getting scrambled if you walk past a strong magnet. Though they mention new materials like antiferromagnets might help solve that.
Okay.
And just making sure the whole system is thermally stable. Heat is always an issue in electronics, especially when things get dense.
So robustness, reliability, and making it huge. Standard engineering headaches, but on a tiny, complex scale.
Pretty much. But despite these hurdles, the underlying advantages of spintronics are really strong compared to some other technologies being explored.
Like what? What makes spintronics stand out?
Well, Meros et al. Emphasize its clear strengths in right energy, right speed, endurance, and stochasticity, meaning it uses very little energy to learn or update information. It's fast, it lasts a long time through many cycles, and it even has a bit of inherent randomness, stochasticity, which can actually be useful for some AI learning techniques.
Interesting. Sometimes randomness helps.
It can, yeah. Helps avoid getting stuck in bad solutions during learning. And remember that CMOS compatibility we mentioned.
Right, works with existing chip tech.
That gives it a clear pathway to manufacturability. It's much easier to imagine mass-producing this compared to something totally alien to current factories.
Okay, wow. That was quite the journey into these magnetic brains. Let's try and pull out the key takeaways for everyone listening.
Sounds good.
So, first takeaway. Neuromorphic computing isn't just about software. It's about building fundamentally different hardware. Hardware that mimics the brain's structure to slash energy use and boost speed for AI.
Right. Moving beyond those old, inefficient von Neumann designs for AI tasks.
Second, spintronics using electron spin, those tiny magnets, is a really promising technology for actually building these brain-like components. Things like magnetic tunnel junctions or MTJs.
Especially when you can make them multi-state, like Razut's team did, to act like nuanced synapses.
Yeah, and that's the third point. Researchers like that team in Poland have already built and tested hardware neural networks using these spintronic synapses and neurons. And they've shown they can perform complex tasks like reading handwritten numbers with really high accuracy and incredible energy savings compared to previous approaches.
It's proof that the concept works, and works well.
So looking at the big picture here, where does this lead?
I think we're genuinely on the edge of a major shift in AI hardware. Seriously. Imagine your phone, your smart devices running really complex AI, but using barely any power, like brain levels of efficiency.
Powered by tiny magnets.
Powered by tiny magnets. It's not just about making current AI faster or cheaper to run. It's about enabling entirely new AI capabilities, things that are just too power hungry to even consider right now.
In everything from our gadgets to, I don't know, robotics, medicine.
Exactly. Advanced robotics, truly smart cities, personalized medicine. When you remove that massive energy barrier, it opens up possibilities we probably haven't even thought of yet.
Which leads to a pretty mind-bending final thought, doesn't it? If AI could run with the power efficiency of a human brain, what kind of truly intelligent, truly autonomous systems could we create? Things that seem like science fiction now. Maybe even companions.
What problems could we solve if energy wasn't the main limitation for intelligence?
Something to ponder. What really stood out to you in all of this? We genuinely love to hear your thoughts. Thank you for joining us on the Deep Dive today as we explored this incredible place where magnets meet minds.